Welcome to this explainer. Today, we're exploring the hidden, fascinating world of manufacturing by tracking the journey of molten metal. And we're not just talking about pouring a glowing liquid into a hole here. Absolutely not. What we're really looking at is a high-stakes race against time, temperature, and fluid dynamics. To get a perfect solid metal part out of a mold, engineers have to manipulate the laws of thermodynamics in absolutely brilliant ways.
So here's our roadmap for this molten journey. First up, we'll look at the anatomy of the mold, followed by mastering the pour. Then we'll tackle the threat of turbulence and fluidity, testing the flow. Finally, we'll break down the science of solidification and controlling metal shrinkage. It's quite the sequential obstacle course, so let's get into it. Okay, let's dive into this. Section 1, Anatomy of the Mold, the very foundation of casting.
We all generally know what a mold is, right? It's a hollow container that gives shape to a liquid as it hardens. But here is the absolutely crucial engineering detail for metal casting. The cavity itself has to be made slightly oversized. Actually, scratch that. It must be oversized. It can't just be the exact dimensions of your final product. Why? Well, because metal inherently shrinks as it cools and solidifies. So the mold has to perfectly predict and accommodate that future contraction.
Now, you might think these extreme temperature containers are all made out of high-tech composites or, super specialized alloys, but look at this list of common mold materials: sand, plaster, ceramic, and yes, sometimes other metals. Sand? Really? Yes, sand is incredibly common because when you mix it with the right binders, it holds its shape, it withstands immense heat, and, best of all, you can just easily break it away once the part is finished. It's a beautifully simple material solving a highly complex industrial problem.
But how does the metal actually get safely into that mold cavity? It doesn't just drop straight in, no way. It travels through something called the gating system. You can think of this as a meticulously designed obstacle course meant to purposely slow down the molten metal's kinetic energy and safely guide it. It starts up top at the pouring cup, drops down a vertical channel called the sprue, travels horizontally through the runner, and finally enters the main cavity through the gate. For really large castings, they'll even use multiple gates. The entire goal here? Strict, absolute control.
Moving right along to Section 2, Mastering the Pour. This is where we set up that delicate thermodynamic balance.
Once the gating system is prepped, we reach the main event. But first things first, we got to talk about temperature, specifically this concept called superheat. Superheat is the temperature difference between the state at which the metal is poured and the melting point where freezing or solidification actually begins. Think of it as a thermal buffer. It represents the exact amount of thermal energy that has to be removed from that molten metal before it even starts to solidify. If your superheat calculation is off, the entire process fails before it even really begins.
And then we have the volumetric pouring rate. This right here is the ultimate Goldilocks pacing challenge. If you pour that molten metal too slowly, you lose your superheat way too fast. The metal will literally chill and freeze prematurely, blocking up the gating system before your cavity is even full. But on the flip side, if your pouring rate is too fast and aggressive, you introduce severe turbulence into the system. It really has to be just right.
Which brings us to Section 3, the threat of turbulence. And trust me, things can get chaotic fast.
So what exactly happens if we get overzealous and pour too fast? Well, you can think of turbulence as the ultimate party crasher. When the fluid flow gets agitated, irregular, and chaotic, it actively destroys the quality of the casting. First, it accelerates the formation of metal oxides, and those get trapped inside the solidifying part, creating dangerous weak points. Second, all that violent churning promotes the absorption of gases, leaving microscopic bubbles or voids. And third, all that erratic, high-velocity liquid literally impacts and washes away the internal sand or plaster surfaces. It aggravates mold erosion and totally ruins the final shape.
Section 4. Fluidity. Testing the flow. Let's see how engineers outsmart that turbulence.
Now, what's really interesting about this slide is how we actually measure the metal's flow. To guarantee a smooth pour, engineers measure a property called fluidity, which is basically just the inverse of viscosity. It's a measure of how well the metal can conquer the mold and fill every tiny crevice before getting, well, lazy and freezing. To test this in the real world, they use the standard spiral mold test. They pour molten metal into a central sprue and let it flow outward into a spiraling channel. It's a literal race against the clock. The metal keeps flowing until it loses enough heat to freeze solid. So visually, a longer cast spiral definitively proves that a specific metal has greater fluidity.
All right, slowing things down a bit for Section 5, the science of solidification, transforming from a turbulent liquid to a stable solid. So after the high-energy journey of the pour, the metal finally comes to rest inside the cavity. But figuring out how long it takes to completely freeze isn't just guesswork. It relies on this heavy, foundational, yet brilliantly simple empirical relationship known as Choronov's rule. This formula tells us that total solidification time depends entirely on the ratio of the casting's volume to its surface area. It's that simple. The larger the volume compared to the surface area, the longer it takes to cool.
And this brilliantly illustrates exactly how different geometries drastically affect cooling time. Let's look at the math for common shapes. If you keep the volume constant, the surface area changes wildly depending on whether the shape is a cube, a cylinder, or a sphere. A sphere has the lowest possible surface area for a given volume, meaning it's going to hold onto its heat the longest. But a shape with a high surface area, like a flat plate, that's going to shed its heat and freeze much faster. Engineers literally have to calculate these volume-to-area ratios for every single section of a complex casting to predict exactly how the whole thing will cool down.
Finally, Section 6, controlling metal shrinkage, the inevitable contraction.
As that phase change happens and the heat escapes, the metal inherently contracts. It's just physics. But shrinkage doesn't just happen all at once. It actually threatens to ruin the casting in 3 distinct stages. Stage 1 is liquid contraction. As the molten metal cools before freezing, it shrinks in volume. Stage 2 is the big one, solidification shrinkage. That's the massive contraction occurring during the physical phase change from liquid to solid. And then you have stage 3, thermal contraction, which just keeps happening as the now solid part cools all the way down to room temperature.
So with all that shrinking going on, how do you prevent a part from just cracking or deforming? You use a really clever engineering solution called the riser. Remember Choronov's rule from a minute ago? Well, engineers intentionally design a secondary reservoir attached to the mold, that's the riser, and they give it a significantly larger volume-to-area ratio than the main casting. Because of that specific ratio, the main casting solidifies first. As it shrinks, it actually pulls still molten metal from the riser. The riser effectively sacrifices itself, freezing last, just to backfill the shrinking casting and make sure the final product is flawless.
So, the absolutely crucial point to take away from all of this is that casting is this deeply orchestrated dance of physics. The next time you see a heavy piece of machinery, an engine block, or even just a simple metal tool, I want you to ask yourself, look around you. How many everyday objects rely on this exact, invisible balance of fluid dynamics and thermodynamics for their structural integrity? It is honestly incredible to think about the precise math and thermal control hiding inside the objects we rely on every single day. Thanks for joining me on this explainer, and keep questioning how the world around you is made.